Well, good morning, everyone. This is the 14th of September, and this is ME3228, and this is officially video number 4 that we are going to start off with today. And this is video 4, but it's actually the whiteboard number 1 that we so many of these boards we use up on this video. But at any rate, this is all going to be starting something new here. We're going to start talking about mechanical testing methods for material selection, and you're going to be starting to do that in your labs with 3 of these, and we're going to go through 3 of these. But essentially, there are 6 basic performance criteria that are used to select engineering materials for structural applications. And I've listed them here for you. And they're no particular order necessarily, but there is strength, there is heat resistance, fatigue resistance, toughness, wear resistance, and finally corrosion resistance. And it actually makes a good little list, a little outline for you anytime you're doing a mechanical component design for, again, structural applications. These are 6 criteria that you really should look at in your design for the material properties. And the ones that I've got asterisks, strength, toughness, and wear resistance, those are the ones that you're going to be using tests for in your lab experiments and or doing a report on. And so the strength, of course, is what we're going to cover this morning, and we'll get into that in a moment specifically. But that essentially uses the tensile test, and we'll talk about all the various types of strengths that come from this tensile test. And then toughness, you're going to be looking at that. Although this is sort of you can also get a little bit of at least a comparison value, a rough estimate on toughness when you look at some of the results from the tensile test, which again we'll talk about. But toughness tests specifically involve impact tests, and primarily using the Sharpie IZOD testing method. And you will be seeing that utilized in your experiments as well. And finally, we'll talk about wear resistance. Wear resistance, of course, involves hardness tests, and the specific one we're going to be using is the Rockwell hardness test. So these are all real key, significant criteria when trying to choose a particular material for an application, for a design application. Now, briefly, heat resistance. We're not going to go over these in great detail because we're going to try to emphasize the ones that we actually do reports on and experiments on. But heat resistance, of course, is very, very key in many different types of applications because, and this is primarily for metals. But heat resistance can be a factor, especially when we're talking creep, and especially outside the realm of metals when we're talking polymers. That can definitely be an issue with respect to what his heat resistance might be. And some of them are very, very low heat tolerance, and some are high heat tolerance. So it's something to consider, especially if you're having a piece of equipment or a design component that's going to be going into some kind of an environment where, especially when that temperature starts to change back and forth. So we need to look at heat resistance, because if that continues to happen, we could have, with respect to this one, heat can actually be a fatigue stress. So especially if it's going back and forth from high heat to low heat, that could essentially be a thermal fatigue stress initiated that way. So at any rate, so heat resistance is something necessary, and they have, again, standardized tests to do this with. As this says down here, that all of these criteria have standard tests have been developed to measure these properties. So there's some for heat resistance, there's some for fatigue, there's obviously some for corrosion that we're not going to go into particular specifics on. But again, fatigue resistance, we all know that fatigue is one of the, if not the most important factor involving mechanical failures. There are far more fatigue failures, mechanical failures, than any other type of stress that we encounter. So this is something definitely to determine what materials have good fatigue resistance as opposed to others, and what we might be able to do to make that better, to enhance that particular property. So at any rate, let's see. Well, I got this goofy timer that didn't go off. At any rate, so toughness is the one we're going to talk about specifically, and probably not today in this first video, but next video I'm sure we'll talk about specifics of the toughness test involving, again, the impact tests, Sharpie and IZOD specifically. Wear resistance, again, is something very critical, especially for mechanical elements, all different types of motions, transferring of forces from one mechanical element to another usually involves mating pieces or parts, shafts, gears, belts, things like this. So wear resistance is very much a key ingredient. And the standard test for wear resistance, specifically for metals, would be a hardness test. And the one we're going to be using is a wide variety of different type of hardness tests, and we'll talk about the variety of those and how they overlap. But we're going to specifically talk about the Rockwell hardness test. And last but not least, the corrosion resistance is something that you have to remember to look at specifically in a design, because everything goes out and usually in some kind of a adverse environment. So you need to know the material from a material standpoint, what its overall corrosive resistance would be in a specific type of environment, be it heat, hot and cold, be it humidity, be it chemical, whatever it might be. So you need to know what kind of resistance this particular material might have to these corrosive environments that it might be entering into, and what type of materials you might want to choose to resist that corrosion resistance. So there are corrosion resistance specific standardized tests for that. Okay. All right. So let me remove this board and get this will be still video number 4, but it'll be board number 2. Let me make sure, get this aligned with the camera so you can see this. Since I don't have a chalkboard to write all this about, I have to just write it on this whiteboard, and I'll make sure you can see this. Okay, now a moment ago on that first board, the light kind of glared on that word applications, engineering material for structural applications. This one, the light is kind of looking like it glaring under understood by. And then also down here, this is the word tensile. So tensile here and understood by, the two words are kind of glared out by the light we're having to use here for the board. Okay, so back to mechanical test methods. And again, out of those 6, the first one that they talked about, and probably the most common one, ultimately is strength. And strength is a wide, big, umbrellistic type of term, especially for mechanical engineers. But it most commonly refers to those strengths that are determined by a tensile test or a tensile test, which is conducted at a constant rate of loading. Now, I'm going to go through the actual test mechanism and go through the mechanics of that here in a little bit, but let's just kind of get some foundational information out here up front, and then we'll talk about specifics. But again, it's conducted at a constant rate of loading. These strengths are best understood by examining what the result of this, the data that is derived from this tensile test, is what we call a stress-strain curve. Now, I know you've heard that term, of course. Also, it could be called stress-strain diagram. But the tensile stress-strain curve is constructed from a load / elongation measurements made on the test specimen. So again, when we get to see what this looks like, you'll see what I'm talking about with respect to the actual. You're going to be reading two sets of data on this test. You're going to be reading load data, as indicated here, and also you're going to be measuring elongation of that specimen as it begins to pull apart. Because this is a tensile test where you're trying to pull something apart as opposed to compressive. Although this test, even though it's a universal tensile testing machine, as you'll see, can also be used for compressive testing. But right now we're just talking about tensile testing. Okay. Now, stress. Of course, you're going to be able to calculate the stress based on the load that this machine is giving to that specimen. And we know stress is force divided by area. So what you're going to be looking for are the force data points on this diagram as this load progresses. And then, of course, the area will be that cross-sectional area of whatever that specimen might be. And I'll show you some samples of those specimens here in a minute. So any rate, so the stress is calculated from the load measurements and the dimensions of the specimen to get the area. So and normally, in these what we call engineering or nominal stress strain curves, we are using the original dimensions. They are used in the calculations, which basically means we're just going to disregard any kind of thinning or necking down during that testing. So this results in, what we call a nominal or engineering stress. All right, something to remember. Now, if we were to use the specific dimensional changes, then that would be something we call true stress and strain. All right, but for the most part, 9 times out of 10, we're going to be just referring to this nominal or what we call engineering stresses, derived again from this tensile test. So strain is something else, of course. It is normally calculated from the elongation measurements and the original length of the specimen. And so because we're going to be elongating something, and this elongation you're going to see is going to be the foundation for a specific property other than strength. Okay, so and we'll go through that here in a moment, But again, the strain is just calculated from the elongation measurements and then also from the reduction in that area as it begins to pull apart and thin out and what we call necking down. And you'll see an example of that here in a minute. Okay, so the shape of that stress strain curve or diagram is an indication of both two properties here, design properties that we're going to go into in detail probably sometime next week maybe, of strength and ductility. So again, this tensile test is such a wonderful test because you can get so many different areas of information. So we're going to be looking at different strength indicators and also ductility indicators, again, from this tensile test. And the initial straight portion of that curve, specifically on metals primarily, represents stress levels that do not produce plastic deformation. Within that straight line portion of that curve, which I'll draw one here in a minute, the straight line portion is basically elastic deformation, where beyond that you begin getting to plastic deformation. So the slope of this portion of that straight line of the materials is called the modulus of elasticity, or Young's modulus. Okay, that's the straight line portion of that, and which also you could say if a material has that definitive straight line portion where it has an elastic region, it obeys what we call Hooke's law, and I'll get into the derivation of that later too. Or you can more commonly refer to that material as a Hookean type material, meaning that it has a definitive elastic region and a plastic deformation region. Okay, so, and the thing you need to realize is that the steeper the slope, the stiffer the material. Okay, the steeper the slope, the stiffer the material. Okay, So that's kind of a summary of the test and or the diagram. So let me give you some specifics on the test. I need to take a minute and erase this board here briefly and talk about the actual tests, the strength tests. That you can use some of this information, of course, for your reports. All right, so let's look at this. And let's look at, again, this is ME 3228, and this is going to still be video number 4. Okay. And so what we're going to look at here is the standard ASTM tests for determining strength of metals. So we're going to be looking at the standard ASTM, which is American Society for Testing and Materials tests for determining strength of metals. Strength of metals. Okay. All right. So what I'm going to do is I'm going to list over here the property that we're testing for, the actual ASTM standard. This is the actual standard, and this is what you need to know. This is the actual ASTM test standard number, and then what the overall scope of this test involves. Okay, so let's talk about the first one, the property meaning tensile, a tensile property. And here is the standard. This is a standard tensile test. Is called an E8. All right, it's an E8 test, an ASTM test number. All right, this is ASTM standard test number. All right, and what's the scope? What in other words, you derive from this? You're going to get tension or tensile strength. All right, you're going to get yield strength. You're also going to get, again, we talked about, you're going to get elongation. You're going to get information regarding the elongation of that specimen. You're also going to get reduction of area. Okay, that's the scope of what you're going to get from that. Now, we won't do this necessarily, but there are other tests. There's another tensile test, and its number is E557, and that's basically tensile tests that are for aluminum. This is primarily for steel-based products, but this is tension tests for aluminum and magnesium. Tensile tests for aluminum and magnesium. Okay, and then, like I said, you can also do a compressive test, and that number is an E9, and you can do it off most machines are capable of doing both. So that's an E9, and of course you would get compressive tests. Okay. So I think basically I'm running out of time on this particular video, but what I'm going to do is I'm going to pick this up from here and talk a little bit more about from what this E8 test, what we can obtain following specific information, specific data points, and then get into the actual stress strain device, and we'll do that on the next board, which this is board number 2. And so video number 5 will begin to look at, again, a little more specifics as to what this E8 test derives, as well as looking at the actual stress strain testing mechanism. Okay, so we'll stop it here and be back to you soon.